Good morning.
Good morning, Justin.
Good morning.
Good morning, Doctor.
Good morning.
Good
Good morning, Deb. Good morning, Deb. Okay, go. So let's see. Okay, now before I continue, does anybody have any questions? It can be from anywhere. It doesn't have to be from. No? Okay, well, that's something. And please take a note of this. Nice to say that this is your. That's okay, huh? Vector Doppler. And let's say that, okay, yes, we have a let's say positive Doppler shift. Okay, in a graph. Where we mainly can say that, okay, yes, of the flows in the blood, this here is going to be as okay, the maximum positive Doppler shift, or I guess that's okay, velocity. Is that clear? Whereas we can say it's okay, this part of the graph here, for instance, in this case here is going to be as okay, we can say it's okay, the minimum and this here, okay, it's positive, that's okay. Doppler shift or velocity. Right? Now my question is, in a blood vessel, at what time or what stage of the phase do we have a maximum velocity?
And this is for the blood vessel.
Yes,
I would say at stenosis.
not at stenosis, in a normal healthy vessel, my dear.
Oh, okay.
At the end of systole. What happened during systole, ladies?
Contracts
What contracts?
the vessels, the heart. Sorry. No, heart.
It's going to be the heart that contracts. That's what we call systole, right? So this here is actually going to be as okay. Oh, this part here is actually going to add mark what we know as okay in systolic velocity or speed. Is that clear? Now everybody is okay should be able to guess is okay at what stage do we have the minimum velocity in a vessel?
Is it the diastolic?
Exactly related to the diastole. At end of diastole. Well, what is this? That this is going to be referred to as the end diastolic velocity, or you can say speed. Did you guys get that?
Can you repeat
Yeah.
that?
The velocity that we record here. There's a mini graph where it's okay as we go up like this, it's okay. There's going to be an increase in the number. Similarly, ladies, as we go down here, it's okay. The numbers is going to, it's okay. There'll be a okay increase in the number. Okay. Although it's okay, these are going to be as okay in negative Doppler shifts. But the actual value of the number 10, 20, 30, 40, 50, 60, that is going to increase because in Doppler is okay, the plus and minus mainly only indicates the direction, right? So we can even say it's okay if we, for instance, okay, recorded a negative Doppler shift. This is still just going to be as okay your maximum. In this case, as okay a negative Doppler shift. But that will still just okay happen at end of systole of the heart. Yeah. Whereas okay, as this velocity here is okay, that's going to be as okay the lowest negative Doppler shift. Okay, which means okay going to okay be at the end of diastole. Did that make sense?
Yes, it did.
Good. Okay. Because okay, you go here. This is 0. I mean, you just go and count 1, 2, 3, 4, 5, 6, 7. You say, well, okay, this is still 0. This becomes okay. -1, -2, -3, -4, -5, -6. But that's okay. And this being a regular graph of anything, yes, okay, because it's okay. Minus values will be yes, okay, lesser than positive values. But it's okay. In Doppler, yes, okay, means it's okay. There's nothing wrong with having okay as a negative Doppler shift. There's not going to be a plus point of having a positive Doppler shift because the plus and minus only as okay indicates the direction of the blood flow. Are they is okay towards the transducer or away from the transducer? And it's very easy. For instance, yes, okay, say, well, okay, yes, we have a blood vessel. Okay. And let's just say, okay, yes, if this is okay, was your color map. It's going to be very easy to say, well, okay, yes. So, or actually, yes, okay, you can say very easy to make a positive Doppler shift in the same blood vessel. Here, become negative. That's all you do. Yeah, we can say it's okay here. It might be flowing at a speed of the speed of solid is okay. Maybe let's say it's okay 20 centimeters per second, for instance. Well, okay, that speed is going to be the same here. 20 centimeters per second. But when we as okay convert this speed into Doppler shift is going to be as okay plus 20 centimeters per second. Why is it plus? Mainly because in this case here we had a positive Doppler shift. Clear. Whereas over here, it's okay, the Doppler shift is going to be, yes, okay, 20 centimeters per second, but it is going to be negative. Why negative? Mainly because here, it's okay, the blood flows away from the themselves. But the positive and negative mainly is going to, it's okay, be determined by the direction in which the blood flow. Where we say, it's okay, this is your home line here. This is your home line here. And we mainly said that, okay, as the blood flows towards the home line, that's when you have a positive Doppler shift. So here we can actually say that, okay, the blood flows from left to right. You still have, okay, the flow from left to right here as well. But mainly it's okay, you end up having a negative Doppler shift in the same muscle. Mainly because it's okay, the blood flows away from the home line. So the blood is still flowing in this direction. It's the same vessel, but it's okay, you steer the angle from this angle to this angle. Or was positive become negative. Okay. Any questions yet? So you guys clear that, okay, as what is closest to your baseline in a spectral Doppler will be your end diastolic velocities.
Yes.
And what is on the top of the peak of your SOK spectral graph, if that's what you want to call it, is going to be SOK your max velocities, which will be at the stage of, at the end of systole. Mainly because you say, it's okay, what's going to be the end of systole when, okay, as the systole has finished, the heart has fully contracted. Right, okay, that's going to be the stage at which, okay, yes, the blood in the vessel, or we can say the amount of blood in the vessel is at its highest. Whether you go to, yes, okay, the end of the diastole, that's where there's going to be lesser blood in the blood vessel and more is filled in the heart. And this blood mania is okay. Yeah, so that's when the blood is going to be flowing at a lower speed in the blood vessel. Now when, okay, yes, so this is going to be the end of the diastole. Now the heart contracts again. And at the end stage of systole or contraction, that's where the velocity will be at its max in the blood vessel. And max is going to be, okay, that top point of the graph or bottom point of the graph. All depending upon whether you had a positive or negative Doppler shift. Okay. There was nothing wrong in having a negative Doppler shift, okay? Yeah, this is not a bank balance. You can say, well, okay, yes. Negative is mainly because, that's okay, the money that you have is going away from you. It's leaving you, right? Okay. Okay. And positive, yes, okay. The money is coming towards you. Okay, girls. Just some point, yes, okay, I remember, yes, okay. Yes, you may say, okay, Mike, you should sleep a little bit more. But it struck my head in, it's okay, 3:30 this morning or in the night. That's okay, before I start anything, let me make sure that I bring this point on. Okay, girls? So hopefully it's okay, I have cleared my conscience now. Okay, Ghost. Now let's talk about what we call spectral analysis. Okay, and well, okay, that's the main things about spectral analysis. It's mainly going to be now primarily what we'll see is going to mainly be related to to your spectral Doppler. Now what we already know that as within a blood vessel. Within a blood vessel is at different points throughout the blood vessel. Your blood is going to be flowing at different velocities. Clear? Okay. And you can primarily say that's why your graph may be like this. Because I had it flowing with a persistent same velocity throughout. Well, the key says you would have a graph that would have been like this. Okay. Now the spectral analysis mainly is going to be it's pretty much as you can see, it's a computer system, which means it takes the different velocities at different points of the blood vessel and individually represent them on the spectral Doppler. Clear? Okay. Now this is not something that you can adjust or anything. This is something that pretty much happens. You can say it's pretty much automatically. Okay. And the two basic methods of a spectral analysis is what we call fast Fourier transform. And the other one, although I don't agree that this here is a spectral analysis, mainly because it is mainly related to color Doppler, or what they call autocorrelation. Now, what you may see in your book that they say, this fast Fourier transform here, that is mainly we can say an updated method of spectral analysis, which is mainly pretty much we can say digitalized. Okay. Now, what your book does do is if you go on page 325. And what it does say is it mentions something about early methods of Doppler analysis. Or spectral analysis was something that they called zero crossing detectors. Okay. There's even something that they call chirp Z transform. Okay, and then last one was going to say what they call time interval histograms. So these are mainly we can say the predecessors of what we now call fast Fourier transform. Okay. Now the reason that I mentioned them is you can say, okay, now these are mainly as okay, they're all earlier methods, so they are mainly as okay going to be obsolete now. But you may as okay, we'll see as okay questions in the exam review. Or as okay, chapter review where they ask about these. Okay. Contra to yes, okay, your FFT, your fast Fourier transform. All these fellows here were not digitalized, but they were analog. Is that clear? Okay. Any questions? Any questions, girls?
No.
Good. Now let's just take as okay, what in the blue is fast Fourier transform. And we can mainly say, okay, one of the main benefits of okay, as fast Fourier transform, which is okay, that's a form of okay, a spectral analysis, is, as we said earlier, now, well, okay, not only as okay, does the spectral analysis as okay, we can say it's okay, give us, let's say it's okay, the idea of, let's see, it's okay, our maximum and minimum velocities. In the blood vessel. Right? But what it also does, it also gives us, okay, as the idea of whether we had a laminar flow versus let's say, let's do this one. Turbulent flow. Did that make sense?
Yeah.
Clear? Okay. Now on a color Doppler, let me just ask. If we say it's okay, color Doppler. Now we for instance, okay, may use whatsoever color map. Where we can say, for instance, okay, yes. This may be as okay, the less negative or less positive and max positive velocity. And we can say it's okay. This may, for instance, okay, be the minimum negative And we can say it's okay. Maximum negative velocities. Did that make sense? All dependent upon us, okay, the blood vessel. Okay. Then we were recording a dark color Doppler. This kind of map here is okay, we call that velocity color map. Now, which maps? Gives us info of the flow. That's just okay, flow pattern. Which color map gives us okay as the flow as okay? Enable us to just okay record not only the velocity but also the flow pattern to distinguish whether we have a laminar flow versus turbulent flow.
The variance one?
Pardon me?
Variance?
Variance map, exactly. Very good. Okay. Okay. Where we as okay said, okay, yes, on a variance map, it was going to be the colors on the left side that were just okay indicate laminar flows, where they were positive or negative. Whereas okay, if we had, let's say, yes, okay, for instance, let's say that we have these colors here, it's okay on the right side. That will be positive turbulent flows. And we can say, okay, if you have this, let's just say, yes, okay, these will have been negative turbulent flows. But that was okay, it's in your color Doppler. So the question does arise as, okay, how does a laminar flow appear on a, that's okay, spectral Doppler? And how is it that, for instance, okay, a turbulent flow is going to just okay appear on a spectral Doppler? Now, girls, let's see. Can you guys see this?
Yeah.
Okay, girls. Now, ladies, This one here. That is a laminar flow. Okay. And what we actually is okay can see here, let's do it this way. This area here. This area here is okay. That's what they actually is okay called the spectral window. Okay. And what the spectral window is, if you see here, it's okay, it is clear. Clear in the sense that, okay, yes, it is okay, having the same color as the background. Black. So yes, okay, in laminar flow, yes, okay, we mainly say it's okay that we have a clear spectral window. If you also, yes, okay, look at the graph. It goes like this. Or we can say, it's okay, this line here. And this line here. Or this line here, yes, okay, are thin. So these are mainly, yes, okay, indicators of a laminar flow on a spectral Doppler.
I have a question.
Yeah,
You said what about the lines?
the line. If you look at the outline of, okay, of your graph here, it's going to be, it's okay, relatively change, yes, okay, what you see over here. Okay, this fellow here. That's an example of, okay, as turbulent flow. Is that clear? Now, if you look at, okay, as the outline of, okay, as your graph, if you look at the outline of your graph here and compare it to over here, the outline of the graph is, it has, okay, it's a thick outline, right? Is that clear?
Yeah.
Good. Although not shown in this picture here. But if that's okay, if you look on, that's okay, you can say figure, 19.43 in your book on page 336. What you also will see is that, okay, yes, your spectral window. The spectral window, which was mainly as, okay, this area here, for instance, this area here is filled up with mainly as, okay, what would be noise. Or even as, okay, this area here is filled up with that's okay, small bright dots, which is noise. Or you can say, okay, the spectral window is appears foggy. Whereas also, okay, over here, you can say it's okay. Or what did we say over here? The spectral windows, they were clear. Did you guys get that? Now this whole thing is okay, mainly is okay, we can say it's okay. The broadening of the outline of the graph. And, well, okay, yes, this unclear, yes, okay, spectral window, or we can actually say, okay, that it appeared foggy, is going to be referred to as, together as, spectral broadening. And what spectral broadening is going to, yes, okay, indicate is that, okay, yes, in this case, yes, okay, well, okay, these are our velocities, yes, okay, all dependent upon, yes, okay, how yes, okay, our graph go up and down. Okay, but we are not having a laminar flow, but the flow is rather going to be turbulent. Did that make sense? Clear? Okay. So we can mainly see as, okay, what would a normal spectral Doppler look like? Normally, and okay, what's going to be as, okay, because it's okay, a normal spectral Doppler, where we mainly as, okay, have a laminar flow. Clear? What we will have is, that's okay, we can say it's okay, a thin outline of our graph. Right, okay. So a thin outline of the graph, or it's okay, which actually is going to be okay, the measurement of the velocity. And another thing was that, okay, as we said, okay, yes, all this is okay, these were, say, what we call is okay, it's okay, the spectral windows. Which we, okay, in our diagram is marked as, okay, these circles here are clear. Okay. But what you just have to realize that, okay, yes, the background, or yes, okay, your whole spectrum is going to be black. It means, okay, going to be as, okay, white lines that are going to, okay, appear on your spectral Doppler as the recording. Just as you see here. This here is, okay, that is your spectral recording on the black background. This or this or this here is, okay, that was your spectral window. We mean is, okay, when we say is, okay, that they are clear is that, okay, as we don't have any recording or nothing is being, yes, okay, shown there. So the mean is, okay, just appear as, okay, have the same complexion as the overall background of your spectrum. Did that make sense?
Yeah.
Right, okay. So you have clear spectral windows. Right, okay. So that's how it's okay, that will appear, or you can say, okay, a normal laminar flow will appear on a spectral Doppler. So the spectral windows are going to be clear. Whereas if we had, okay, yes, a turbulent flow. Okay. Now, what we mainly will have is that, okay, yes, we can say, okay, that the outline is going to be as okay. So what we have is, okay, as we have a thick, or we can actually say, okay, see a broad outline of the graph. And what we also will have is that, okay, yes, the spectral windows are, we can say, okay, here going to be unclear, mainly because, okay, they're going to, okay, be polluted with. It's okay, a lot of, okay, yes, white dots, like this. But generally, it's okay, what they say that, okay, both of these, yes, okay, that's what the word for two as, okay, yes, spectral broadening. Although, yes, okay, it's mainly, yes, okay, logically speaking, it will mainly, yes, okay, just have been this alone, yes, okay, which should have been spectral broadening because the outline of the spectrum is broadened out. Now, have any of you ever used an ink pen? Not a ballpoint, but an ink pen.
Yes.
Good. And my dear, what happened? What happened if you, for instance, yes, okay, run your finger or hand or sleeve or whatever on the ink before it dried?
I think it smears.
It smears. So you can say, okay, that would be, yes, okay, spectral broadening of the ink. Did that make sense?
Yeah.
Right, okay. Although, yes, okay, you have written your name in nice calligraphy. Okay. You have written your name in nice calligraphy. But yes, okay. If you run your hand on it before, it's okay, the ink has dried. It may become something like this. Yeah. So this will be as okay, where we can say, okay, we're having spectral broadening. Now, girls, one thing. This is what you will have as, okay, as a result of, okay, as spectral broadening. Clear? Okay, that is only going to be, please keep in mind, only going to just be the spectral windows. That would be unclear. Practically, yes, I showed it to you girls, or you can actually see it, it's on your figure 14.3. But it is mainly going to be as that. Okay. Sorry, that's your spectral window. Okay, that the spectral window actually is is going to have some sort of yes. It's small dots here, like this. So this will be spectral broadening. Okay. Okay. That yes, where your windows are unclear. I mean, yes, appear for because of yes, a lot of small reflections in the spectral window. Did you girls get that?
Yeah.
Why are you not clear? Now, let's just say, let's say here, for instance, that you got all over the place. All over. Now, ladies, this can't be spectral broadening. Right? Because you had a laminar flow. So your question is, as how is it that, as my spectral windows are unclear? But what you also see as in the other areas of the background is going to be as all this. This is mainly because it's we actually have too high of Doppler gain. Now, since this is going to be as on a spectral Doppler, we actually is we call that as a spectral Doppler gain. And then we actually call it, you can say, all is the whole of your what you want to call it, spectrum. That's actually is as contaminated by noise. So all these is small is fellows here is actually is noise. Where did they come from? That too high gain of your Doppler. So it means says that too high is going gain of the Doppler is means going to be too high amplification of the Doppler signals. What do you say about amplification? Signal to noise ratio was even or equal. Are you girls getting that? The same can also, yes, okay, happen on a color Doppler. Well, let's not go there yet. Yeah. Now, some of you may say, okay, how can we, for instance, okay, make, let's say, okay, the spectral Doppler too high? Now, generally, as okay, on our keyboard, as okay, we had these two Doppler functions, right? So one was color flow, although yes, okay, the other one here is going to yes, okay, be wave as pulsed wave, which means okay when we turn this one here on. There you will see that okay, yes, you get a spectral Doppler. And ladies, just like your B mode, which okay is cause your general amplification or your brightness. When we yes, okay, turn this clockwise, that increases the amplification. So if we yes, okay, do the same over here, turn this one here clockwise, that is just going to yes, okay, increase the yes, okay, amplification of the spectral Doppler. And that's going to call it as the whole background is going to yes, okay, because I get contaminated by noise. So the way to yes, okay, to get rid of this is, well, okay, yes, you can just turn this knob here anti-clockwise, because that's going to yes, okay, reduce the amplification of the Doppler signal. But yes, okay, also reduce the noise. Is that clear? That's fine. We will talk specifically about it in chapter 20. Clear? Okay, girls. Now, 4 or 5 points which are not written in your book. So just make a little note here. Or we can say it's okay, additional note. You have plenty of space. Right, okay. And the thing that I'm going to say is, we can mean it's okay, just call them imposters of spectral broadening. And what would be an imposter?
Something that acts like something that it's not.
Right, okay, so you can say that's okay, things which may look like spectral broadening, but actually aren't spectral broadening, which mainly means yes, okay, it may mimic or it may look like a spectral broadening, but actually it's okay, we are not having a spectral broadening, which mainly mean that we are actually not having you can say it's okay, turbulent flow. But it's okay, some mistakes that we may commit while taking a Doppler or doing a Doppler recording may actually elicit something that looks like spectral broadening, but which is not. Clear? So the aliases of spectral broadening are artifacts that mimic or looks like spectral broadening or spectral broadening. Sorry. Now, one reason that we may develop imposters of spectral broadening is because what we just talked about, that the Doppler gain is too high. But okay, ladies, the word is mean it's okay. Yes. This gain here was mean it's okay, just it says okay, amplification of the Doppler signals. So if we keep that, it's okay. If we make that too high, what is it that we get? Okay, shit. Where was it? I said we got noise all over the place. Clear? Did that make sense? So that may be an imposter of your spectral Doppler, which may may give you an impression that you have a turbulent flow. Sorry. Yep. Another thing, another imposter is going to be that this is poor Doppler angle. Picamania says closer to 90 degrees. Angles is going to more likely give you spectral Doppler or spectral broadening, sorry. Here. Another case going to be too big sample gate size. Now, if you remember, when we talked, for instance, pulse wave Doppler, we said, now whenever we turn on a pulse wave Doppler, we get a sample gate, which is this fellow here. Clear? Okay. Is that clear? Is that clear?
Yes.
Good. Now, this size of the sample gate here can actually, be increased. And it can also be decreased. Now, ladies, if you look at your practical sheet, one of the last things that is mentioned, and that is going to be as okay, I think as it's going to be as okay, spectral volume or something like that. Okay. Now, some of you will ask, okay, how can we increase or decrease the size of this gate here? Now, mainly that's okay on your touch screen. At the bottom down here is actually is okay, going to be as okay, something that says okay, S volume or something like that. Where you actually is okay with the help of touching that can actually is okay, increase the gate size. Okay. So each time you touch it, just okay, it may just okay increase a little bit. Clear? But as okay, if you make it, for instance, it's okay, you can say as okay, too big. What that actually is okay may cause is that you end up having something that is okay, it looks like spectral darkening, or spectral broadening, sorry, but which isn't. But you may think, oh shit, do we have okay as a turbulent flow? No. Fellow, you just need to just okay reduce the size of the gate here because it is too big. Is that clear? Is that clear?
Yes.
Good. Now you can say it's okay. The last imposter of okay a spectral broadening is that we as okay say that okay as this same very sample gate here is too close to the vessel wall. Which may lure mean that okay, yes. Let's say that okay, yes, this here is okay as your blood vessel. Okay. Where you may say is okay. If for instance, it's okay, the sample gate is kept like something like this. That is going to be too close to the vessel wall. Even yes, okay, if you take the sample gate all the way down here. Okay, that is still going to be as okay, too close to the sample vessel wall. And what is that going to cause? That's going to as okay, produce a spectral recording that is going to as okay, mimic spectral broadening and may give you this okay, or may make you think that okay, yes, you have a turbulent flow. No. The trouble is mainly because okay, you place the sample gate in a not ideal position within the vessel. That is too close to the vessel wall. So ideally goes as okay, and you most likely as okay will hear your teachers as okay in yes okay your vascular scanning. Is okay as whenever you record a velocity, it's okay, keep the gate in center of the vessel. Did that make sense? Okay. So some of the teachers just okay, you can say, okay, what if I kept my gate like okay, somewhere here? It's okay, you got okay as a velocity, but they'll say no. It's okay, but it's not good enough because I want you to keep the sample gain in the middle. So that's okay. If you think I'm on your nerves, that's okay. Just wait. Okay. So yes, okay, keep it in the center. They will require you to do so. So these were the 4 imposters of spectral broadening. So too high samples, too high as okay. Doppler gain. Clear? Okay. Poor Doppler angle. Too big sample gate and okay, yes, and or if the sample gate is too close to the vessel wall. So you can always say yes, okay, good is good, but then too much good is bad. So too big, too high gain, and too close to the vessel wall here. Yes, okay, your 3 imposters right here, the 3 stooges. Okay. And then the third was okay, we just have to okay, make our 4-1, which is going to be okay, your poor Doppler angle. And you can say it's okay, the closer you are to a 90-degree, the poorer the angle. What was the ideal angle for Doppler? Yes, ladies. Where the measured velocity is equal to the actual velocity. Yes, girls. At which angles is the measured velocity equal to the actual velocity?
Is 0 degree or 180?
0 degree and 180 degree, exactly. Why? Now I'm becoming an a-hole. Why?
Because it's equal to 1.
What is equal to 1?
The angle at 0 degrees.
So if I give you $1, you will give me $180?
No,
Okay. I have a lot of $1 bills or even $10 bills or $100 bills that I want to exchange with you. You're right in one part, but you're missing the vital info.
I don't know the other part.
The
Sorry.
cosine theta value of those angles was 1. Which
Yes.
angles? 0 degree and 180 degrees, right? Right?
Right.
Okay, girls. So that was all that I could offer for Doppler. Yes, Shaq, you raise your hand, my dear.
Maybe I missed it, but did we do the audio correlation?
No, that's mainly going to be for color Doppler.
All right.
Okay. And you can actually see that, okay, it mainly said, okay, autocorrelation is used with color Doppler. Okay. Just one thing, and okay, it's actually written in the second part of the sentence. They use this, okay, enormous amount of data to be processed. And that data is going to be as okay, a lot of sound waves. Which mainly mean that autocorrelation of color Doppler compared to spectral Doppler exposes the patient to more energy and is going to more likely cause
Bioeffects.
effects. Here we go. Okay, ladies. Now, what you have at the end of the chapter here is 24 questions. Okay. Now, ladies, if you have paid a little bit attention to what I have been talking about for the last couple of days, okay, I try to went slowly and steadily through this chapter here. I hope I didn't speed too much. So it's okay that we got aliasing because somebody couldn't follow along. Clear. So yes, okay, goals. Have any of you okay paid the least amount of attention to yes, okay, what I've been saying? You should have no problems answering these questions here. But I will still give you ladies, okay, yes, 20 minutes to do them. And you can have, okay, 10 minutes to, yes, okay, make your coffee or whatever. So I see you ladies in half an hour at 10:50. And we will look at these questions here together and play a little around with them as well, okay? Okay, ladies. Now don't spend half an hour drinking coffee. Okay, so have fun till then. Okay, ladies. Good morning. Sorry. Good morning. Welcome back. Here goes that. Did you get the chance to do the questions?
Yes.
Okay, how were they?
Um,
Some of them I
Okay.
had to read twice,
yeah.
3 times.
Is not a
what they were
good
asking.
sign. Or means turbulence ahead.
Yes.
Right. A little bit turbulent.
Okay.
Balloons.
Okay, let's see if we can get that into a laminar flow, okay? And for it to be a laminar flow, yes, okay. And not an imposter spectral broadening. Well, okay. I need to be in the center. Okay, girls, look here. Usually the first couple of questions are always easy. Let's see. Now, the Doppler effect is represented by as a dash when the source and the receiver are dash. Now here is okay, ideal is okay. This was a question that you were given, and okay, yes, you were your test. You were given okay options, okay, different options. What could be in option 1 and dash 1 and 2. But the Doppler effect meaning it's okay. What we just call is okay a Doppler frequency. Which you also, as okay, can call a Doppler shift. Okay. Now, actually, it's okay, is a frequency. Right, okay. And when we mean to say that, okay, is that the source. Now, please keep in mind here, go, that's okay, the source is what it has been from the beginning of this book. Your transducer. And, well, okay, yes, all this, okay, it says receiver. Okay, well, that's okay, yes. Should be tissue. Oh, no, sorry, it's going to be here. The T source is going to be, it's okay, the tissue. Okay, the receiver here is going to be, it's okay, the transducer. But maybe that's okay where we say that okay, as both of these, or one of these here is in motion in relation to the other. Clear? Okay. And the shift of the frequency, well, mainly that's okay, there's that difference between it's okay, the reflected frequency from the transmitted frequency. Clear? Okay. So the whole thing about Doppler, well, okay, it was going to be okay, the difference between these two frequencies. But where that's okay, ultimately it's okay, is going to it's okay be shown as a velocity, which was made as okay, just how fast is the motion. Not just how fast, but also as okay, in what direction. And the direction comes into effect as okay when we as okay comparing it as okay the reflected frequency versus the transmitted frequency. And we said that the direction could either be positive or it could be negative. Now we had a positive Doppler shift if your reflected frequency was greater than the transmitter frequency. And vice versa. Yeah. Where we can mainly say as okay, greater difference. Or practical as okay, between the two frequencies here is going to lead to as okay, a greater Doppler shift. And that greater Doppler shift is mean yes, okay, indicated okay the blood flows at a greater speed. Whereas okay, if there was a low difference between yes, okay, these two frequencies, that will mainly be a low Doppler shift, which mainly yes, okay, indicate that the blood is flowing at a low speed. And then a high speed can be positive and negative. And a low speed as well also can be positive and negative. Did you girls get that? Yes or no?
Yes.
Okay. Let's look at question 2. So starting from the same point, the sound source is moving towards east at 12 miles per hour. So we can say it's okay. We can say it's okay, this is the starting point. Right. Now maybe that's okay, just to understand this one here, it's okay, let's just make a compass. Where we say north, south, west, and east. So starting from the same point, a sound source is moving towards east at a speed of 12 miles per hour. That was your source. And the receiver is moving toward west at 10 miles per hour. Okay, now what they mean is, okay, just ask us, okay, yes. In this case here, it's okay, is your Doppler shift positive or is your Doppler shift negative? Now the main thing that, okay, as I mentioned that back then when we talked about Doppler shifts, positive and negative. Mainly because, okay, in the light of, okay, these questions here, that we can say, okay, positive Doppler shift is if the distance between is okay, over here is okay, can call is okay, the source or receiver and source is decreasing. Where, okay, is going to be a negative Doppler shift is okay, if that same distance between is okay, okay, we can say the receiver and source is increasing. So if one person is traveling towards west and another person is okay traveling towards east, okay, as they travel, the distance between them is okay will increase in time. So that will mainly mean that okay is there's going to be a negative Doppler shift because of the increasing distance. Clear? Even, yes, okay, if this fellow here, let me say, okay, that, okay, yes. The receiver didn't move, but okay, yes, this fellow here is okay, still travel towards east. Or he could have been traveling towards west. He could have been traveling towards north or south. But maybe it's okay because he is moving away. It's still going to be as okay negative because the distance increases. But as okay, since they're traveling okay opposite directions, you can say it's okay by hour and hour. Yes, okay, they start at the same point. After 1 hour, there's going to be as okay a 12-mile distance or 22 miles difference between yes, okay, where they are. At the end of 2 hours, is going to be as okay a distance of 24. No, sorry. Yeah, 44, and so on. Okay. But it's mainly as okay because the distance between yes, okay, the two things that we're talking about here is increasing. That will be as okay a negative Doppler shift. Did that make sense? Did that make sense?
Yeah.
Yes.
Good. Now you go to question number 3. And again, we can say it's okay starting from the same point. Okay, the receiver moving toward west at a speed of 12 miles per hour. Clear? Now it goes again and says, okay, the source is moving towards west at a speed of 10 miles per hour. Now, some of you may be scratching your heads because they may ask, okay, asking us the same. Is this a positive Doppler shift? Or is this a negative Doppler shift? Well, dear, it's a negative Doppler shift. Because, okay, we both started at the same point. Although, yes, okay, we travel in the same direction. But you can say it's okay, after 1 hour, or we can say it's okay when the race started, if you want to put it that way. There was just okay, they were at the same point. So we can say it's okay, the distance between them was 0. After 1 hour, do we still have yes, okay, mainly because one traveled at a speed of 12 miles per hour and the other traveled at a speed of 10 meters per hour. There was a 2 miles distance between the two. That is after 1 hour. When you go to yes, okay, after 2 hours, that's okay. This fellow here is okay, may have traveled okay as a total distance of okay as 24 miles. Whereas okay, this fellow here only has okay because he traveled at the same speed. That's okay, just a travel distance of 2 miles, 10 miles per hour. So in 2 hours, you are traveling 20 miles. So now that's okay, the distance is even greater. There's a 4 mile distance between. So mainly because the distance increases between as okay, what we call as okay, the source and receiver. That's why it's okay, it's a negative Doppler shift. Although it's okay, they are traveling in the same direction. But had they, let's put it this way, that they start at the same point, Clear. Receiver, yes, okay, we say yes, okay. Travels west at 12 miles per hour. And source, yes, okay, also travel at a speed of 12 miles per hour in the same direction. What is going to be a Doppler shift now? Will it be positive? Will it be negative? Yes, girls. Will your Doppler shift be positive or will it be negative?
Positive.
Okay. So Shaq thing is positive.
Wait,
Okay.
so that both says 12 centimeters. I mean,
Same,
both
yes,
says
okay,
12.
same speed. They travel at the same speed in the same direction. You can say
Yes.
miles per hour, kilometers per hour, centimeters per second. It doesn't really matter. Let's just okay as miles per hour for both of them.
So yes, my answer stays the same.
And okay, in this case, yes, okay, they both travel towards west as well. So you said you would have a positive Doppler shift. Okay. Any other guess?
I think it will be no shift.
No shift.
Yeah, they
So you
move
say 0?
0.
Oh, okay. Okay, let me just make this short. Does anybody think there's a negative Doppler shift?
I say positive.
You think positive too? Okay. So nobody is negative. Girls. Is 0. Why? Because the distance between them is not increasing. If it was increasing, yes, okay, then we would have had a negative Doppler shift. But neither is the distance between them decreasing. The distance between them remain the same. So there's a 0 Doppler shift. So just think of it, yes, okay. We are standing at a point, or let's say it's okay, somebody is standing at a point and something, yes, okay, comes towards you. That is positive because the distance decreases. They walk away from you, the distance increases. That will be negative. But if yes, okay, if you walk side by side, the distance doesn't increase or neither does it decrease. So if something doesn't increase nor decrease, it remains constant. So yes, okay, that will be a 0 Doppler shift. Did that make sense?
Yes.
So yes, okay, it's just a question which yes, okay, can be asked, and you hear how? Well, this is how. So in this case, yes, okay, the Doppler shift would have been 0. Okay, ladies, let's look on question number 4. Now, Doppler shift produces information about. Now, all yes, okay, Doppler shift was, okay, it's a shift in the frequency. And what we mean by shift was that, okay, yes, it could either increase or decrease. But that shift in frequency is actually, it's okay, going to, it's okay, indicate the velocity. And as I said earlier, a greater shift means higher velocity. Lower shift will mean lower velocity. Where, okay, we talk of, okay, at the direction of shift, or it's okay, the shift in terms of which is greater. And which is lower will determine whether we have a negative Doppler shift or a positive Doppler shift. A positive or negative of a high value, of a low value. This here means yes, okay, this is the direction part of velocity. Where we can say it's okay, this becomes yes, okay, the numerical part of velocity. Where it will be as okay, any certain number, we can say okay, 200 miles or 20 miles per second, for instance. Whereas okay, here this could be as okay directions. North, south, east, west, or that's okay in our velocity, and the Doppler is going to be okay towards transducer, away from transducer. Is that clear? Question 5. At what angle between the sound beam and the direction of the motion will the Doppler shift be highest? And that's what we said earlier. 180 degrees angle. And that is okay as if your transducer was scanning from here and the blood flows in this direction. That will be 180 degrees. Where you say it's okay, 0 degrees. We can say it's okay. That was, for instance, okay if you're scanning from here, but the blood flow is in this direction. Both these angles here, yes, okay, had a cosine theta value of 1. Whereas, okay, your whole Doppler shift equation, that 2, okay, is fixed. The velocity of blood times, okay, as the transducer's frequency times the cosine theta angle. All this here is going to just, okay, be multiplied by the greatest number, which was 1. Whereas if we go from 0 degrees to 90 degrees, we actually, it's okay, we'll see it's okay that the cosine theta value of the angles decreases. Because we go from 1, just okay, we had an angle of 30, we say it's okay, that was 0.87. Then we had, okay, an angle of 60. We said, okay, that had a 0 cosine theta value of that angle was 0.5, which is a half. And then we went 90, which was 0. Whereas, okay, when we go from, let's say, it's okay, 90 to 180, what we mainly see is, okay, that the cosine theta value actually is, okay, of the angle is, okay, increases. Because at 90 is, okay, it was 0. But then we see it's, okay, 120, that's where we had 0.5. Clear? That's when you go as okay to, let's say, as okay 150. It was AKS 8.0. Just give AKS a minus and minus. Okay, likewise, okay, so here, for this one here is okay. Here was -1, and here was +1. So it's okay, 180 was going to be as okay, a cosine theta value of -1. Yeah, okay. But you don't necessarily as okay have to remember the cosine theta value of, let's say, these angles and these angles here. Likewise, as okay as 30 and okay 60. Okay. Well, when your angle is greater than 90, that will be negative. From 90 to 180, those will be negatives. From 0 to 90 will be positives. And 90 is just 0, 0. Did you ladies get that? Okay. So you're not going to get a question that's going to ask you, okay, what is the cosine theta value of, okay, a 30-degree angle? No. So that's okay. Our next question, that's okay. That's what we already asked. Answer. Okay. At what angle between the sound beam and okay, at the direction of the blood flow is okay at having a Doppler shift closest to 0. And that's not going to be at a 0-degree angle. That is going to be at a 90-degree angle, because a 90-degree angle had a cosine theta value of 0. Now, please, ladies, okay, this will be required to know. Okay?
Yeah.
Good. Question number 7. And okay, what is the speed difference between speed and velocity? Now, I have probably as okay talked about this so many times that okay, as you should be able to say that in your sleep. Okay. Taking you goes on, okay, yes, road trips to, yes, okay, whatever places. So speed is just the numerical value with a unit. Where the unit is fixed, any unit of distance per unit of time, that becomes speed with a certain value. Clear? Whereas velocity can be the same speed, but as okay, that's contagious there, with different directions. So then a speed at which you are traveling is also as okay specified with the direction in which you are traveling, it becomes velocity. Did that make sense? Clear? So what is the speed of sound in soft tissue? What is the speed of sound in soft tissue? .54 millimeters per microsecond. Or 1,540 meters per second. Ladies, this is bad. That was the only speed that you were told to. Yes, okay, remember. I'm not going to ask what the speed of sound is in the lung. Let me just say, by the speed of sound in lung greater than that of soft tissue or lesser or equal. The sound travel at a speed that is greater than the speed of sound in soft tissues in the lungs or lesser. That's fine.
It's lesser. It's like 500 meters per second.
Okay, thank you, dear. You didn't need to give me the number. Okay. Thank you, Tatiana. Question number 8. Now, what is the current method of processing Doppler signals? And that was your FFT. Or what we just talked about is, okay, fast Fourier transform. Question 9, all this, okay, and that's something that we mentioned and okay, that's in the text. Well, that's okay when we did it. But what it means is, okay, where is the normally is okay Doppler shift? Which means, okay, could be as okay, either an increase in the frequency or a decrease in the frequency. When comparing SOK transmitter frequency versus reflected frequency, transmitter frequency versus reflected frequency. Which means SOK will be SOK anything between 20 hertz to 20 kilohertz. And we can say, okay, this will be okay the lowest Doppler shift. And okay, this one has okay can be okay the greatest Doppler shift. Which means okay will be okay what will be the Doppler shift? The difference between these two. Okay, but you can also see as okay, there's a cheat to remember this one here is okay because where was it that these two here were? Here were as okay the audible, the range of audible frequencies. Now that doesn't mean that your Doppler shift becomes audible. Okay, but we can say, okay, that's okay, it's a cheat. So if we say, okay, there are mag, that's okay, transmitted frequency, for instance, okay, was, let's say, it's okay, 1 megahertz. Then we may say, okay, we have a increase in the frequency. It means, okay, causes, okay, the reflected frequency to be, let's say, it's okay, 1.02 megahertz. That means it will mean that, okay, we had a change of, okay, as 20 kilohertz. Where, okay, it's increased by 20 kilohertz. So our reflected frequency is greater than transmitted frequency. Which means, okay, in this case, it will give us, okay, as a positive. And because it's okay, max positive Doppler shift. Question number 10. Now the phenomena where high velocities appear in the opposite direction. Now, guys, please keep in mind here, it's okay that it talks of high velocities. And these high velocities is okay, appear in opposite direction. Where we could say it's okay, if this high velocity here was positive, but it appears in negative. Or if this high velocity here is okay, for instance, okay, was negative, but it appears in positive. Or B is okay, what we call aliasing. Did that make sense? Now, this question here can also be asked in a pattern that we see is okay. And we can say, okay, a high velocity. Or we can say, okay, a Doppler shift. That is greater than the Nyquist limit. Is called what? Okay, girls. Any questions so far? Now, a frequency or the frequency at which aliasing occurs is called Nyquist limit. Just look at it in this way. Because I mean, it's okay, it's like what's going to be this. This was your Nyquist limit. Or you could say it's okay. For instance, it's okay. This was going to be, it's okay, your Nyquist limit too. Okay. So the frequency at which aliasing occurs is Nyquist limit. So if you don't reach the Nyquist limit, well, okay, then you don't have aliasing. So that's pretty much okay as what it's going to, or what it's asking about. Now, this question here can also be asked in a fashion like, okay, yes. Yes, okay, the lowest frequency of aliasing is known as what? The Nyquist limit. Okay. Question number 12. Okay, yes. The area of interrogation in a pulse Doppler exam is called. The means, okay, it says, okay, when we use pulse wave Doppler. Okay. What do we call the area where oopsie Doppler shift is determined? Now, whenever we turn around, yes, okay, a pulse wave Doppler, you will see this dude coming on, which is okay called the sample window. Yeah. Now, if the same question was asked, but if we just change this word out here to yes, okay, a continuous wave Doppler. And what do we call that area? Yes, ladies. The same question, but the pulse wave Doppler is replaced by continuous wave Doppler. What will be your answer? Okay, girls. Welcome back, girls. And yes,
It would have like the overlap. If it was
exactly.
a continuous.
Area of overlap, right? Clear? Because it is continuously transmitting and it is continuously receiving. So that shouldn't have taken 5 minutes. Okay. Question 13. And one of my favorite varieties of questions, true and false. So is it correct to say that, okay, the higher the emitted frequency? Now, please keep in mind, girls, that, okay, it's going to, okay, it's a higher frequency. Okay. The next thing is, okay, that's impulsed wave Doppler. That's also another thing where you can, where your legs can slip. Is that more likely? We can say, okay, greater chance of aliasing. Now here it's okay, both of these here is okay. Things here is okay, make it true. Now why do I say both? Because goals, if we just switch this one here, the frequency to PRF, then okay, it's a greater PRF. You will less likely have, or there's going to be a less likelihood of aliasing, right? Because what this increased PRF here was going to do is going to increase the Nyquist limit. And the higher the Nyquist limit, lesser the chances of aliasing. Did you ladies get that?
Yes, so the frequency they're talking about in this question would be referring to the PRF?
Pardon me?
The frequency that they're talking about in this question would refer to the PRF?
No.
No?
Does it say pulse repetition frequency?
No, it does not. It just says frequency.
Exactly. Clear? But it could have been the same question, but okay, as if frequency is changed over PRF, the answer became false.
Oh, okay, I see. Okay.
Clear?
Yes.
Right, okay. Likewise, girls. High frequency, low frequency. Really doesn't matter. But if we say, for instance, okay, change the pulsed wave transducer out with continuous wave transducer. And please keep in mind here, it doesn't really matter whether you say it's okay, a high frequency or a low frequency continuous wave transducer, because in continuous wave transducer, there is no aliasing. Did that make sense?
Yes.
Okay. So, yes, okay, just be watchful. You can't say, Mike, but the question in the book for this question, or the answer for this question in the book was true. You gave it on the test, and now all of a sudden it's false. Well, okay, it's false because maybe I changed the frequency of a PRF. Clear? Or it may become, yes, okay, all of a sudden false because it's okay, I checked that, okay, the transducer, not a pulse wave transducer, it's a continuous wave transducer. Now, just keep in mind here, girls, that, okay, yes, if we have a lower PRF, yes, okay, let's say with a pulse wave transducer, well, okay, of course, it's okay, there's going to be a greater likelihood for aliasing. Because lower PRF mean lower Nyquist limit. And the lower the Nyquist limit we keep, that means it's okay, going to cause that. Even if the blood flows at a low velocity, it may, it's okay, be greater than the Nyquist limit. Or we can say, okay, Doppler shift becomes greater than the Nyquist limit. Did that make sense?
Yeah.
Right, okay. So, yes, okay. Be watchful for things like that. Now we can mean it's okay. So this will mean yes, okay, just yes, okay, you can say it's okay. If you know yes, okay, your Doppler shift equation, we say, okay, here this frequency, yes, okay, that was your transducer's frequency. And if that is greater, you'll get a greater Doppler shift. Greater Doppler shift, greater chances of aliasing. Now, question 14. Again, it's okay, true or false. So yes, okay. Shallower sample volume results in more aliasing. And okay, here we have, okay, now we're saying it's okay, sample window. There's no question about, okay, that's going to be, it's okay, pulse wave Doppler. Yeah. But here they say it's okay, it's a shallow sample window. Is that going to lead to more aliasing? Which means, or I meant that, okay, as a deep shallow, as okay, sample window, or had led to less aliasing. And that is false. Because practically, it's okay for it to be true. Deeper your sample window is going to be, there's going to be a greater aliasing. And vice versa. Mainly because at a shallow gate, or says, okay, shallow sample window, what do you have? You have a low PRP. Very much. It takes the pulse lesser time to go and come back, go and come back, go and come back. Which means, yes, okay, mean that, okay, yes. Indirectly, yes, okay, you have an equally or reciprocally, yes, okay, high PRF. Which means that, okay, as you would end up with, okay, as a greater Nyquist limit and greater Nyquist limit. Less aliasing. Well, here Kamei says, okay, well, okay, the Nyquist limit means, okay, is shorter because you kept it at a shorter depth, a shallower depth. Whereas for this depth here, that's okay, you have a greater PRP. That greater PRP means, okay, yes, a lesser PRF. Which, okay, indirectly as okay, may reduce as okay, your Nyquist limit and increase aliasing. Okay, or what we mainly said here was that, okay, yes, the sample rate, which is how many samples do you get in a frequency in a unit of time. If that, for instance, okay, was greater than, okay, as the velocity of the blood flowing through the sample gate, and there will be no aliasing. Whereas, okay, ladies, if this was opposite, which is going to be the case here, then you will have aliasing. But pretty much, okay, that chart of aliasing, or chart of aliasing, how to get rid of aliasing, scan at a shallower depth. Or scan from a view from an angle where you can place the sample gate or the pulse at a shallower depth. Did that make sense? Did you ladies get that? So that means yes, okay, just ask about this. Sorry. Yes, okay, chart and leasing here. Any question, ladies?
No.
Okay, question 15, and again, yes, okay. What a blessing. True or false? Now only pulsed wave Doppler has aliasing. And that is true. Oopsie. Because what we've mainly said as okay, as our last thought on aliasing was that we can actually yes, okay, get rid of this aliasing, yes, okay, if we used continuous wave Doppler. Clear? Not to talk, ladies, that's okay. Some of you says, okay, now what about is okay, a continuous wave transducer? Well, okay, this one here as well will have no aliasing. But here, yes, okay, the main benefit for this one here is that this one actually is okay, able to yes, okay, record very, very high velocities. And it's only when we have velocities that were above what we could measure that we will see aliasing. As a matter of fact, that's okay, we said this one here was primarily yes, okay, used for aortic stenosis. It's mainly as okay, it's going to be as okay, a phenomena. Not a phenomenon, actual condition in which is okay, in which your aortic valve doesn't open up completely. So pretty much okay, due to yes, okay, that narrowing, two things is going to happen. There's going to be okay, a super high velocity due to yes, okay, smaller area, right? That continuity equation that we talked about. Another thing that you guess okay, girls will see, and especially it's okay, the girls who are CVT cases. That's where you will see turbulence. So in aortic stenosis or any stenosis, that's okay, you will see turbulence. Okay, but then yes, okay, those velocities can be yes, okay, measured without turbulence, without aliasing, if you or it's okay, visible. If you yes, okay, use a continuous wave transducer. Okay, that little fellow on page 313. You can go to question 16 unless somebody has a question. Is it cold? I just leave it over there.
I did not understand what that line was literally.
Any question, ladies? Any question, ladies?
No.
Question 16. Now what we have here is, okay, yes, an 8 megahertz transducer with a pulse repetition frequency of 50 or 5,000 hertz. So we have, okay, as an 8 megahertz transducer. As a matter of fact, okay, we can make it, okay, just say, okay, this was, okay, pulse wave Doppler. Why? Mainly because, okay, it has a ERF of 50,000 megahertz or 5,000 megahertz. Okay. And an imaging depth of 7 centimeters. Now, what is the Nyquist frequency? So what the main is, okay, just ask us is, okay, yes, where is the Nyquist frequency? And some of you may be scratching your head and say, what the fuck is a Nyquist frequency? Well, okay, girls, what we just have so far called is, okay, a Nyquist limit. Because even as, okay, when you look at the Nyquist limit, it is going to be as, okay, expressed in the form of frequency. Now, and the question here is, okay, you may see that, okay, as I've written two things in black. And why was that? That's mainly because, okay, this information here was mainly as, okay, just to throw you off. Clear? Because the only thing that we needed to, yes, okay, calculate our Nyquist limit or Nyquist frequency was the PRF. Is it 5,000 megahertz? Oh, okay. Sorry. 5,000 hertz or 5 megahertz, right? Okay. Is okay as the Nyquist limit. Then we then can say as okay is going to is okay be divided by 2. That is your, that's going to be as okay your Nyquist limit. So you can mainly say okay 2,500 hertz. Okay, this 2,500 hertz also can be the same as 2.5 kilohertz. Did that make sense? Did that make sense, girls?
Yes.
Good. Next is question 17. So again, yes, okay, what we have is, okay, we have that 8 megahertz frequency transducer. Okay, with a pulse repetition of, okay, as the same. 5,000 hertz. So that is okay as your PRF. Now I'll measure just okay a Doppler shift of 7 kilohertz. So we can measure this okay that okay, so our Doppler shift is 7 kilohertz. Now they say the same study is repeated by okay as a 4 megahertz frequency transducer. What will be the Doppler shift measured? So here we can actually say now this info here is really not what we needed. Clear? And just if you look at, okay, as your Doppler shift equation is going to be as, okay, 2 multiplied by, as, okay, velocity of blood multiplied by transducer's frequency multiplied by, okay, cosine theta angle, and if it says, okay, now divided by, is, okay, the propagation speed. Now in the first case, as, okay, we had a frequency of 4. That means that, okay, what the Doppler shift was calculated out to be is 7 kilohertz. No, sorry, 8 megahertz, sorry. Clear? Where, okay, as now we just half that to 4 megahertz. And then they just ask, okay, what is going to be as, okay, the new Doppler shift. Nothing else changed. So the frequency halved, the Doppler shift will halve. The half of 7 is 3.5 kilohertz. Did that make sense? Right, okay. It could have been the same question where we said, okay, yes, if our initial Doppler shift of 7 kilohertz was, okay, yes, if we had a 4 megahertz transducer, where we actually is, okay, may just, let's say it's, okay, reduces to half of, let's say, okay, 2 kilohertz. Well, okay, the Doppler shift was have been this. Here they actually is, okay, warrants you as, okay, give us, okay, you to calculate a value. Not really calculate, but it's, okay, guess out from the equation here. Which means that's, okay, essentially it's, okay, we halved the frequency of the transducer, so is the Doppler shift going to half. Clear? If you went the opposite way, it's, okay, and doubled it, then, okay, yes. It could have got 14. There's, okay, at a 4, that's, okay, a frequency of, okay, 4 hertz of, that's, okay, yeah, like 4 megahertz. We had, okay, as this as our Doppler shift frequency. If we double it to 8 megahertz, then, okay, yes, the Doppler shift frequency is also going to double and become 14 megahertz or 14 kilohertz. Did that make sense?
Yeah.
Good. So it's mainly as, okay, you can mean it's, okay, the Doppler shift was directly proportional to, it's, okay, the transducer's frequency. So you can say it's, okay, if this doubles, then this doubles. We can say it's, okay, if this, for instance, okay, increase 3 times, then, okay, this is also going to increase 3 times, and so on. And when it's just, okay, directly proportional, that will mainly mean that, okay, yes, if this one here is reduced to half, this will also, is, okay, reduce to half. Something like that, right? Okay. If, okay, yes, your transducer frequency is reduced to 1/3, well, okay, this will also, is, okay, get reduced to 1/3. provided that, okay, of course, yes, okay, everything else was the same. Okay. So mainly, yes, okay, I mean, yes, okay, just questions regarding, yes, okay, the relationships, because I told you, yes, okay, you don't necessarily need to, yes, okay, remember the Doppler shift equation by heart, but at least, yes, okay, know the relationships. Question 17, question 18. Again, yes, okay, what they ask us is, okay, true or false. And what they ask us is a successful Doppler scan, okay, a successful Doppler scan, for example, cannot be performed on a severely anemic patient. That's false. Clear? Okay. The thing is that, okay, yes, you can still perform it. The only thing is that, okay, yes, in a patient that may, yes, okay, be severely anemic, what we may have is, okay, is going to be, yes, okay, a very low Doppler shift. Okay. Why? Mainly because, okay, when we say, okay, somebody is anemic, is okay, he or she has a low red blood cell count. And girls, it's mainly as okay going to be as okay the red blood cells count. That okay as either as okay pass through that area of overlap in okay as continuous wave Doppler. Or yes, okay, through your sample gate or sample volume in a pulse wave Doppler. That is going to, yes, okay, determine, yes, okay, the Doppler shift. Did that make sense? So you can maybe say, okay, a person that may be anemic, that is just like saying, it's okay, well, we have a 5-liter tank. But this 5-liter tank, yes, okay, this person has not been able to, yes, okay, take care of his fish. So there may, yes, okay, just 2-3 small fishes, yes, okay, small swimming around in this tank here. There you can say, okay, these fishes are mainly, yes, okay, going to, yes, okay, be his red blood cells. So that's okay, that will be, yes, okay, anemic. But that person, for instance, okay, has, let's say, it's okay, 50 fishes in that tank. Okay. Then you get 50 fishes, and okay, as in a 5-liter tank is a good amount, at least, okay, not anemic. So that's okay, as the blood flows through here. Or you can say like blood flow through here. That's okay. It's going to have, okay, the number of fishes that passes. So it'll be counted, that determines the Doppler shift. You can still perform it. It may just give you, okay, a false, as okay, low Doppler shift. Did you ladies got that?
Yes.
Pretty. Okay, girls. Question 19. Now, which technique is used to perform spectral analysis on color Doppler data. Okay, so we said, okay, spectral analysis. Okay. Okay, on color Doppler data. Well, okay, that was what we called autocorrelation. Please keep in mind, girls, it is autocorrelation. Clear? So that's okay, on a test like this, or on any test, you may see words where, okay, as it starts with auto, okay, yeah, that's the one. You see as okay, that okay, it's end with shun. Whereas okay, something here in the middle is not correlation or correlate. Because okay, if it said automation, oh, that's not it. Okay. Question number 20. I say, oh, yes, autocorrelation, that will mean yes, okay, related, yes, okay, your color Doppler. On spectral analysis, if you want to put it that way. Which technique is used? Yes, okay, perform spectral analysis on a pulse wave Doppler. A pulse Doppler data. And that was okay, that FFG. Which we just say is okay, it's fast, Fourier transform. Did you girls get that? Question 21. Oh, let's just click this. Now, which of the following terms is synchronous with, okay, yes, or synchronous with a spectral broadening? Now, if you knew, yes, okay, if you know what, okay, yes, causes spectral broadening. Not them posters. Okay, we said, okay, as where did we get spectral broadening? If we had, okay, yes, a turbulent flow. Clear? Yeah, okay, the other options are mainly as okay, just laminar flow. Clear? And then we may just okay, just see that okay, as one says plug flow. And the other says parabolic flow. Well, ladies, both plug flow and parabolic flow were just two subtypes of laminar flow. Where we call plug flow, yes, okay, if the velocity of the blood in all the lanes was the same. Whereas in parabolic, it's different velocities in different lanes, where we may it says, okay, slower towards the periphery of the blood vessel and faster in the center. Question 22. A little weird question, but we can say it's okay. Now, which of the following is an advantage of, okay, yes, a great packet size? Now, please keep in mind, guys, okay, that's what we call Doppler packet, right? Okay, we also call it packet. And what was another name that Doppler packet went under? Yes, girls. Yes, ladies.
Ensemble.
Ensemble, right? Okay. Please keep in mind, girls, I can't emphasize it enough. Please make sure that you know, yes, okay, the synonyms for, yes, okay, different things. Clear. Now here it says less aliasing. No, not really. We say, okay, the velocity is more accurate, but that doesn't mean less aliasing. You can still get aliasing. Okay. Increased frame rate. Well, okay, that was mainly that's okay, the opposite that we got. Because okay, the greater packet size, what do I mean? Greater number of pulses per packet. Because what is it that we said that a packet was? A collection of pulses. So if you make a greater packet, that would mainly mean that we have greater pulses or a greater number of pulses per packet, which mainly is okay. Will increase your G frame. And okay, at the same time, it's okay to reduce the frame rate. Yep. Option C says that's okay, improve lateral resolution. And the reason that okay, it'll improve lateral resolution is wrong. Because okay, lateral resolution is not determined by your pulses, but by the beams or your beam diameter. Clear? Had it said axial resolution, then we could always argue about it. So it's okay, one of the main, yes, okay, advantages of, yes, okay, an increased packet size is increased accuracy of Doppler. Okay, but as I said, okay, there's a very thin line between, yes, okay, you can say it's okay, the packet size that is okay, may is okay, give you an accurate Doppler and inaccurate Doppler. Because your packet size becomes too big, which means okay, we'll call okay as a poor G, as a greater G frame, lower frame rate. Maybe it's okay, just a lower frame rate is going to be That will be as okay again as okay integrated Doppler resolution. Okay. But had they said, okay, as what is the main disadvantage of a great packet size? Then we come in and say, okay, that would have been the answer. This fellow here. Then we will end up with, okay, as a low frame rate. Is that clear?
Yeah.
Good. Question 2 and 3. Now y is, or what I, okay, that's fine. Now here's okay, they give you as okay name that is dedicated, continuous wave Doppler transducer. So sensitive. Now just keep in mind, girls, that okay, as this name here, dedicated continuous wave Doppler transducer is mainly as okay, another name for as okay, that continuous wave transducer that we found on page 313. Where we say that okay, this fellow here, he was a continuous wave transducer, so yes, okay, there was no BM. Or no backing material. So no backing material that causes an increased sensitivity and makes it so sensitive. Did that make sense?
Yes, it did.
Good. Question 24. Like the hours in a day. And okay, yes, we can see our favorite variety of questions. True versus false. Now the lumen of a horizontal vessel this is a horizontal vessel, right?
Right.
Who said right?
Tiffany.
You?
Yeah.
I just see two horizontal lines.
Well,
But that's just assuming that okay, these two lines, yes, okay, presents a blood vessel.
See.
Yeah. Okay.
Yes.
And that's the lumen. Lumen is just a fancy word for a passage. It's evaluated with a color Doppler. So that's okay. If this is the vessel, and okay, yes, it is going to be yes, okay, evaluated by with a color Doppler. So yes, okay, we're going to yes, okay, how color Doppler. But what they say is, okay, sector-shaped image contains a single color. Now, if the shape of your image evaluating this blood vessel here, for instance, was sector-shaped, is this blood vessel here only going to have one color? That says, okay, that this was all okay, color map. No. That would be false. Because okay, in this sector shape image, as okay, there is going to be as okay, even though it's okay, we go color, we will have okay as a sample window. Where okay, yes, on one side of the sample window, that's where we may just have, let's say it's okay, blue, in this case here. It mainly mean okay, this side of the window, it's a positive Doppler shift. Where okay, on the other side of the window here is going to be okay, the negative Doppler shift. And now it's going to okay, be my crazy question. If this was your direction, what is the direction of the blood flow? Does it flow left to right? Or does it flow right to left?
I'll be back.
Yes, ladies. Is there anybody who wants to commit the crime and give an answer?
What kind of Doppler shift do we have?
Huh?
What kind of Doppler shift do we have? A negative or a positive?
That's my question. My question is not that.
Oh,
In this case, that's okay. You have both colors, right?
uh-huh.
So yes, okay. What's going to be the direction of the blood flow then? Because in a sector shape image, you don't have just one color in the option in the answer in your in the image in the blood vessel. That part becomes false.
This is a total guess. I'm going to go left or right.
Okay. But my dear, if this is a total guess, it is a good guess because that is right.
Oh,
Oh, you didn't expect that?
no, my guesses are never right.
Well, something gotta change, my dear.
Right.
Okay. Okay. So we can say, okay, it's the beginning. It's
Yeah.
left to right.
Okay.
Clear? Okay. Now we
Can I
could
ask why?
just pump it up.
Can I ask why?
Why?
Yes.
Because on the positive, on the left side, that's where you have a positive sign, right? So yes, okay. Towards the sample window. Here, away from sample window, which gives you the negative color.
Okay, so the blue is positive and it's going to the sample gate, which is in the green, and it's passing through into the negative.
Exactly.
Okay.
Did that make sense?
So how would it look if it's going from right to left then?
Then the colors would just have been flipped. Had the blood flow been in this direction, then you may never have had, you can say, it's okay, blue on this side, and okay, yes, you can say it's okay, orange on this side.
But the sample gate would still be the same.
Sample gate will still be the same.
All right.
Did that make sense?
Yeah. Just
Okay.
to clarify, we will
Okay,
never go.
just a sec, because there's something that I want you. Because, okay, what can be the change? What can be the change in the question here? That actually is okay, may make this one here, or this question has to become true. And that is going to be as okay, you can say as okay, well, you still have okay as a horizontal, or as okay, the lumen of a horizontal vessel is evaluated by as okay color Doppler. Clear? Okay. So that part of the answer remains the same. Now, where we can mainly say it's okay here. Now you got to be careful. Because, okay, if it says rectangular shaped image, can change a single color. No, that's okay. In this instance, that's okay. What you actually will have is a zero Doppler shift. Because your beam made, okay, yes, that 90-degree angle. Clear? Did that make sense?
Yes.
Good. Whereas, okay, now if we take the other way, and that's why, ladies, you may not always, as okay, get a question. So in this case, yes, okay, what will we have? No matter, as okay, what kind of color map we have. Like this. And let's say, yes, okay, this. Here we have a zero Doppler shift. We will talk more about that tomorrow when we get to chapter 20. But the answer is mainly here because it's okay of a 90-degree angle. Now, if you still read the question the same and say, yes, okay, true or false. So in the first place here, it's okay, it was false. But I say, okay, what can we do to make this answer here become true? Now, we still, that's okay, have the lumen of a horizontal vessel is evaluated by color Doppler. Okay, good. Now here, this, or we can say this. That's where your blood vessel. Ideally, and or is okay, we can say it's okay, ideally. Only will have it's okay, one color. Where we can say it's okay, yes, okay, the image shape is going to be not rectangular, but parallelogram shaped. Did you ladies get that?
Yes.
Now, girls, do I have all of you online? Some of your cameras are off, so I don't know whether you are here or not. If you are here, please turn your cameras on, because we need to set a plan now. So we have chapter 20 to be done. We have chapter 21 to be done. Clear? Chapter 22, which is quality assurance, is going to be a matter of 15 minutes to do that chapter. Okay? Okay, just pay attention, Alicia. That's all. And after that, well, okay, chapter 23, I'm not going to be bugging about that. We already did that during quality. Yes, okay. Sorry. Patient care. So yes, okay. '24. Now, one thing that I want you girls just okay be able to do before it's okay I throw yes okay the next quiz in your faces. Because most of the things that is okay we will talk about in chapter 21. Okay, it's okay, we can do the theory, but the practicals, because there's okay practical aspect, because this is main is okay just a chapter of okay as how do we find polish or Doppler. Yeah, so most of the theory is okay we can do tomorrow. Whatever is left is what due on Monday. But what I would like you guys to do is that we can say it's okay Wednesday and Thursday. And when was your quiz?
Next Tuesday.
Huh?
The quiz is
And
next Tuesday.
Tuesday.
Following, right?
Huh?
Okay.
The 12th.
The 12th?
Yeah.
Okay. Then we just have Tuesday only. That's fine. Well, Wednesday, Thursday, and Friday next week will be in school. Right? So Monday will be zooming, booming. And Tuesday, okay, if you come in for your quiz, if you decide to take it, well, okay. And after that, it's okay. We can still, it's okay, talk the machine. And okay, yes, Wednesday, Thursday, and Friday. Okay. We can even split the session and say, okay, yes, first part of the machine, second part of session, whatever topics. Okay. So
Okay.
is everybody clear on that?
Yes.
Good. Okay, now the word has been passed, but just so you are not confused, yes, okay, you're going to get it written black and white. Okay, girls?
Okay.
Good. See you girls tomorrow.
Tomorrow.
Oh, before, okay, before.
Wait. Yes.
Okay. Please, please, please read on your amplification.
Okay, for tomorrow.
Okay, for tomorrow. Read on your amplification in that chapter 14-ish. Okay,
Okay.
take care.
Are you gonna send the tutoring link for Saturday today or?
Yes, my dear.
tomorrow? Okay, all right.
You'll
thanks.
get those two.
And it's Saturday morning, right?
Yes, morning, my dear.
All right,
Okay,
bye.
okay. Bye, dear.